Hi, good morning, everyone. As the chair of the first plenary lecture, I would like to welcome everyone in this talk. And it is my pleasure and an honor to introduce Professor Kenneth Ribet of UC Berkeley, and also the president of the American Mathematical Society. And then I think everybody knows his academic work, but just let me just summarize in one line, which is totally impossible to but as one of the key main contributor in the foundation of the Parameterizations theorem. And today, so he will talk about the Eigenstein ideal in the theory of modular curves and their Jacobian variety. So please, so let's thanks to the speaker.
Okay, good morning, everyone. Thank you, Sugil, for that very nice introduction. It's a real pleasure for me to be standing here at the KMS DMV joint meeting. I've had many, many associations with the German mathematical community beginning very early in my career when I came to Bonn at the invitation of Fritz Herzebruch as a young mathematician. And I have been to Korea I did go to Korea as early as 1992, but my visits have mostly been very recent, and it's really wonderful to get to know everyone in Seoul and more generally in Korea and kind of find out what people are doing and contribute as I can a little bit. My talk today is about modular forms and modular curves and arithmetic and geometry, and what I want to do is try to make things as simple as possible, and there's really one takeaway, which is that a lot of arithmetical phenomena have their origins in some geometric phenomena, and it's very fruitful sometimes to be able to trace back and forth between the two. So let's get started with something that's going to disappear very quickly. This is kind of a secret slide about what this talk is really supposed to be about, but then all of this notation will be put back in the refrigerator for a very long time. So I've been giving some lectures this week at Yonsei University and at KIAS, and I've been talking about something called the cuspidal subgroup of the Jacobian of a modular curve. And in fact, this afternoon there will be a lecture on that in a special session. So there is some object when we talk about modular forms, which I think are pretty well kind of diffused throughout mathematics. There's a curve that's associated with different spaces of modular forms, modular curves. So these are algebraic curves of some genus. And in geometry, very often you want to study a curve by looking at its Jacobian, which is the abelian variety associated to it. So if you have a curve of genus 5, you have an abelian variety of dimension 5. And the thing is created, one way to make it is to look at divisors on the curve of total degree 0. And you divide out by those that are divisors of functions. If you have a function, it has zeros and poles, and you make the formal sum of the zeros, subtract the formal sum of the poles, and you get a degree 0 divisor because there are as many zeros as there are poles. And the quotient group is called the Jacobian, so if the modular curve is called x0 of n, the Jacobian is j0 of n, and inside of that there's a little finite subgroup that pertains to the cusps. So on this curve, every time you have a curve, there's a marked set of points that are called the cusps. These are kind of the points at infinity that you have to add on in order to make the curve compact. And when you look at divisors of degree 0 that are supported only on the cusps, you have a cuspidal divisor, and the image of all the cuspidal divisors of degree 0 is the subgroup C, which is a finite group. And the main theorem, which we may or may not come to at the end, tells you something significant about C. It has the general aspect of showing that C is pretty big. C is a quotient of a very big group by a very big group, and for all you know, it's the trivial group. We know it's finite. We don't know too much about it in general, and I have a theorem that says that qualitatively, at least, it's as big as you might hope. So in this general direction, just to kind of revisit some history, one of the most famous articles in arithmetic geometry over the last 40 years is Modular Curves and the Eisenstein Ideal by Barry Mazur. So this article won a prize from the American Math Society soon after it came out for having significant impact at the time. And then 35 years later, it won a second prize for lasting impact. And this pertains to the modular curve x0 of n, where n is a prime number, so that's very special. And the cuspidal group had already been computed before Mazur got on the scene. It's a cyclic group of order that's basically the numerator of n minus 1 over 12. It's a group that we all know. And my colleague Andrew Ogg at Berkeley had conjectured that the points coming from this group are the only torsion points on the abelian variety that are acted on trivially by the Galois group of Q, the ones that have rational coordinates. And Mazur actually proved that. So if you want to do some revisionist history, you can say that Mazur proved that the cuspidal group is big. It's big enough to fill up all the rational points, torsion points, although in fact what he proved at the time was that the group of rational torsion points is no bigger than Ogg had conjectured, because all the rational torsion points already come from cusps. And it's kind of remarkable in the subject that a lot of the conjectures that are floating around are now based on numerical calculation. That's kind of a real sea change from 15 years ago, let's say. And one of the key drivers was William Stein, who is a former graduate student at Berkeley, who invented this software package called Sage Math, which is open source and freely downloadable. It's free to everyone, and you can do experiments with it. And of course, he's one of the most prolific experimenters. And one thing he found was some generalization of Ogg's conjecture, also known as Mazur's theorem. He found numerically that all of the rational torsion points of the Jacobian J0 of n, for any n whatsoever, not necessarily prime, are explained by the points coming from the cusps. You have an inclusion rather than an equality, because in general, the cusps are not necessarily rational. They don't necessarily have rational coordinates, and so the cuspidal group is typically bigger than the group of rational torsion points. In fact, one interesting project might be to reformulate Stein's conjecture in such a way that it really becomes an equality and not just an inclusion if you have some characterization of the set of group of cuspidal points in terms of the torsion points that obey some quality, some conditions. And there have been partial results in this direction proving the conjecture. This is all just some history. There was a preprint by Wren over the summer, maybe in May or June, proving it that kind of prime by prime, if you look at the primary components, it's correct. For all the primes that are bigger than 3 and don't divide some number like n squared minus 1. And also, when n is square free, Ota in Japan was actually able to prove this conjecture. But my theme somehow is that up to now, at least, the way you prove conjectures like this was to look at the two sides of the equation or equality or inclusion and say, let's compute both of them and check that they're actually in the predicted configuration. And there is this concept in the subject of proof by pure thought, where you try to avoid explicit calculations and just try to see what you can prove by abstract arguments. So that's something that appeals to me very much, and it kind of motivated the work that I want to describe. So that's kind of the secret beginning of this talk, and now we're going to go to chapter 1, where we start afresh. And here, it's very easy to talk about modular forms by bringing up Ramanujan, because many people know this modular form. If you take the power series expansion that's on the left, q times the product of 1 minus q to the k, and you raise that to the 24th power, you get the discriminant function, delta. That is one of the first modular forms that people encounter. And the coefficients of the power series expansion are called the Ramanujan tau function. And it's really true that Ramanujan studied these coefficients numerically early in the 20th century and made some specific conjectures that were later verified by other mathematicians, especially Mordell. One thing that he noticed, and this is really remarkable how people would notice such a thing, is that you look at the coefficients and modulo the number 691, which is a prime number, the coefficients are congruent to some very standard counting function, namely the sum of the 11th powers of the positive divisors of the index. So for example, if you look at the coefficient of q squared, which is minus 24, that is congruent mod 691 to the sum of the 11th powers of the divisors of 2, which are 1 and 2. And similarly, you look at the coefficient of 4, the divisors of 4 are 1, 2, and 4, and you make the sum of 11th powers, you get a very big number that happens to be congruent mod 691 to minus 1472. And you can check this numerically for 5. There was room enough for that on the slide, and kind of on. And it's kind of remarkable that Ramanujan found this phenomenon and was able to guess that it was true in general. So now you can say, well, what does this mean in terms of modular forms? And it's pretty easy to see what it means in terms of modular forms. So there's the Cuss form, that's the product that I said was typically called capital delta, but for some reason I decided to call it lowercase g because there's also a lowercase f. And the lowercase f is an Eisenstein series. It's maybe the 0th modular form that you would encounter if you studied modular forms, because for the full group of matrices SL2Z, there are Eisenstein series of weights 4, 6, 8, 10, and so on. And 12 is kind of only 4th or 5th on that list. And if you get up to 12, then there are two things you can compare, the F and the G. And the Eisenstein series has as its constant coefficient some number that you might recognize as basically the value of the Riemann zeta function at minus 11. In general, it's the zeta of 1 minus k, where k is the weight. And you have to divide that by 2k. And the zeta values, as we know from Euler, are Bernoulli numbers. They occur in the power series expansion of x over e to the x minus 1. And the 12th Bernoulli number is the very first number in the series of coefficients that has a numerator. The numerator is 691. And what it means for f and g to be congruent mod 691 is that if you take the difference, you will get a power series whose coefficients are all integers except for the 0th one. If you ignore the 0th one, then the integers term by term are congruent mod 691. And the 0th coefficient is really congruent to 0 mod 691 in the sense that it's a rational number whose numerator is divisible by 691. So this is a congruence between two kinds of modular forms, Eisenstein series and Cuss forms. And this could be the first example of a congruence linking modular forms of different kinds. And the fact of the matter is that it's not very hard to prove this congruence between f and g. The way you do it is by what Sarah calls the Sherlock-Holmes method. What could f be congruent to? Well, f, if you look at it, mod 691 kind of starts with 0, so it has the general affect of being a Cuss form, and you say, well, can we actually prove that it's congruent to some Cuss form? Answer, yes. You do a little bit of algebraic manipulation, and then the Sherlock-Holmes method is, which Cuss form is it congruent to? Well, the space of Cuss forms in this case is a one-dimensional complex vector space, so it's not very hard to figure out the coefficient of g. The thing you have to multiply g by to get the congruence is the number 1. So you can prove the congruence that way. And I guess I can kind of make some general propaganda for the fact that looking for different explanations for congruences. In this talk, the explanations often involve kind of physical points of some geometric object, but I think an astute observer would really say these physical points are just homology classes with values in the group of integers mod n for some n. And if you get away from weight 2, if you want to look for a physical explanation for the kind of congruence that we have from Ramanujan, then you really have to look at cohomology. And in fact, the name that comes to mind is Günther Harder. Harder used to talk a lot about Eisenstein cohomology and how Eisenstein cohomology can kind of interacts with the integral structure of the cohomology group associated to some full space of modular forms. So that's really the topic here. And what I next want to do is kind of rephrase the congruence between two modular forms in terms of the congruence between different spaces or different rings of Hecke operators. The rings in this case are both the ring of integers, so there's not a lot of fancy stuff going on. I explained in my talks earlier this week that Ramanujan conjectured a number of identities among the coefficients of that modular form G. For example, the function tau of n that gives the nth coefficient is multiplicative in the arithmetic sense that tau of a product of relatively prime integers is the product of the taus. And this phenomenon was proved, I mean, it was a conjecture of Ramanujan, it was proved by Mordell by introducing Hecke operators on the space of Cuss forms. Basically, you can do it in general, but in his case, he just had a one-dimensional space, so everything was very easy. So we just kind of admit that starting with Mordell and then running through Hecke and Shimura and other mathematicians, people have introduced operators on spaces of modular forms, and for modular forms of one variable, these operators are integers indexed by the positive integers, and they're typically written T sub n. T sub n is the nth Hecke operator. And the two modular forms, f and g, which appeared on the previous slides, are both eigenvectors for the Hecke operators. We call them eigenfunctions. And what's amazing about them is that the Hecke operators are rigged up so that when you have an eigenfunction up to some scaling by a constant, which in both of these cases turns out to be the constant 1, what happens is that the nth eigenvalue is the nth coefficient. And so if you want to talk about congruences between coefficients, it's just the same to talk about congruences between eigenvalues. And here are the formulas that if you hit f with Tn, you get a sub n of f, and if you hit fg with Tn, you get b sub n times g, and a's and b's are just the coefficients of f. And you can see this slightly strange notation, which is common in the subject, that when you apply the operator, the vertical bar is called slash. You slash by the operator, and you write the operator on the right for some reason. And it doesn't really matter that you're doing that because the operators commute with each other, and so whether you have a right action or a left action is completely irrelevant. And I will confess that I have no idea whatsoever in the subject how people started writing the operators on the right-hand side. So back to the subject at hand, if you think about this ring of Hecke operators on the two-dimensional space of modular forms of weight 12 for SL2Z, these operators produce pairs of eigenvalues. Every operator has a pair of eigenvalues. Tn has the pair an, bn. T has the pair ab. And what happens is that the two eigenvalues are congruent to each other mod this number 691. So if you create the ring of Hecke operators on the two-dimensional space, then the restriction to the one-dimensional lines generated by these two eigenvectors gives you a way of embedding or mapping T anyway to Z cross Z, and the image turns out to be exactly this ring R that I introduced at the top of the slide, namely the set of pairs congruent to each other mod 691. So you could ask, why is it no smaller? Why is it not the pairs congruent to each other mod 691 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1? Well, you could have a general theory for that, but in this case, everything is completely explicit, so you can just check the images of a couple of Hecke operators and see that there's no systematic congruence for all Hecke operators aside from the 691 congruence, and leave it at that. Okay, so that was kind of chapter 1. We started off with modular curves, and then that was chapter 0. Chapter 1 was about Ramanujan and 691. And now we're going to go back toward the initial subject, which has to do with geometry of curves. But you don't see that at first. You just see another kind of space of modular forms. So basically, if you study modular forms for the first time, the very first example might be that you have weight k and the full modular group SL2Z. And then the second example might be that you have weight 2, very small weight, but then you have to shrink SL2Z into some congruent subgroup. And a typical congruent subgroup is called gamma 0 n, capital N. It consists of the things that are upper triangular mod n. So if n happens to be 37, which it seems to be on the slide, then gamma 0, 37 is the set of matrices in SL2Z that happen to be upper triangular mod 37. And now we're going to take the space of weight 2 cusp forms for this group. There's also an Eisenstein series, which is not so different looking from the F on the previous slides. But we'll just fix attention to the cusp forms. In the example with 691, the space of cusp forms was one-dimensional. Here, it's two-dimensional. So we really can kind of look at the two dimensions and see if internal to that space, there's already some interesting congruence. And it turns out that there is, if you look at the eigenfunctions for the Hecke operators, up to scaling, you scale things so that the initial coefficients are 1, you get two forms, which I again call F and G. And it's pretty apparent from the first coefficients that the forms for each index have the same parity with their coefficients. So for example, the third coefficients happen to be odd, and the fourth coefficients are even. It looks like there's 2 odds and 3 even on this very short series development. But there's a congruence mod 2. And it actually is the case that the F and the G are congruent mod 2 in the same sense that the F and G previously in the other example were congruent mod 691. And here's the geometry. You may kind of remember from Fermat's last theorem that one of the key things was that when you have cubic curves over Q, so here are 2 elliptic curves, that they are associated with modular forms. That's what Andrew Wiles proved partially in collaboration with Richard Taylor. But already before they did that, there was this whole subject started by Achler and Shimura, where you would start with some group like gamma 0, 37, and you would look for elliptic curves that were associated with that group. And here are the 2 elliptic curves up to some normalization. And the theorem of Wiles and Taylor in this context is that there are no more elliptic curves of conductor 37. These elliptic curves have conductor 37. The conductor is supposed to be the same thing as the level. There are no more modular elliptic curves than the ones that were produced by Eichler and Shimura. And geometrically, the connection between the elliptic curves and modular forms can be expressed by a map, a covering map. So there's a modular curve x0 of 37 that has genus 2, complete algebraic curve over Q, and it maps down to each of these elliptic curves. And you can normalize things so that the map is really unique. There's a point on the modular curve called infinity. That's one of the 2 cusps in that case, and you send it to the 0 point of the elliptic curve. And you also, as I'll explain in another slide, you kind of, in some cases, have to replace the elliptic curve by something that's similar to it, so that the the covering map induces a map between the Jacobian and the elliptic curve that has a connected kernel instead of just a finite group, as it's could in general have a non-connected kernel. And anyway, if you look at the coefficients of these series, the whole point is that the coefficients of the series are related to the arithmetic of the elliptic curve, in the sense that when you take the elliptic curve and you count the number of points that it has over a finite field, like the field with 5 elements in this example, you can figure out the number of points by looking at the 5th coefficient of the series. So for f, for example, the 5th coefficient is -2, and what this tells you is that the number of points, in general, it's kind of 1 plus p minus ap, that's the formula. And if you take 1 plus p, which is 5, minus -2, you get 8. There are 8 points on f mod 5. And for g, because -2 is replaced by 0, there are only 6 points. And I've actually listed the 6 points, which might be fun. A lot of them come from the fact that if you try to solve the equation f, you can take x to be 0, 1, or -1, and the right-hand side is 0, and you can take y to be 0 or -1, and then the left-hand side is 0. And in fact, that's probably everything that there is. No, there are more. There are, well, oh no, f has 8 points. So there are the 6 points I just named. There's a point at infinity, and there's one further point as well. And g has fewer points, but it also has a more complicated looking equation. Okay, so now here are the coverings from the modular curve to the elliptic curve. They're called modular parameterizations. And if you pull back, you get copies of the elliptic curve E sub f and G sub f sitting inside of the Jacobian of the modular curve. And the normalization that I alluded to a few minutes ago pertains to the fact that when you do this pullback, you actually get an embedding, not something whose kernel is a possibly non-trivial finite group. And so what's going on here? You have J037, which is a 2-dimensional abelian variety, and it's a group. You can add and subtract things. And inside of that, you have 2 one-dimensional abelian varieties, E sub f and E sub g. And it would be kind of very natural to think that J037 is the direct product, or direct sum, whatever you want to call it, of these 2 subgroups. And that's almost true, but it's not quite true. And in fact, what happens, let's see if we can get it, well, it's going to be in the next slide, that these 2 elliptic curves sitting inside of J037 are not kind of completely independent. They overlap in points of order 2, and that's the origin of the congruence several slides back between series. They have coefficients that are congruent to each other, mod 2. And you can say this in different ways. First, here's a recap of the congruences among coefficients in terms of the ring of Heck operators. So the ring is again embedded in Z cross Z, just like the ring for the Ramanujan example. It's because the 2 one-dimensional eigenspaces are, they have integer eigenvalues, the coefficients of f and g respectively. So T is embedded in Z cross Z. In the previous example, it had index 691, and here it has index 2. The 2 entries, instead of being congruent mod 691, are congruent mod 2. And the question is whether or not there is some geometric phenomenon that underlies the fact that the T is not a full product. And let me just say, for emphasis, the T kind of acts functorially on everything around it. It acts on the Jacobian, and if T were literally the product, then the Jacobian would just kind of fall apart as a direct sum of 2 one-dimensional subvarieties, and these would be, of course, E and F. And the fact that T is not a product allows for the possibility that these 2 subvarieties actually have something to do with each other. They don't totally make a direct sum. And the kind of surprising takeaway is that what's allowed actually occurs. Namely, there is some interplay points by points between the two elliptic curves, E sub f and E sub g. So the answer is that there is something geometric going on. The curves are fused, that's a good word, in the sense that they share two division points. These are points of order 2. And as I said to you more toward the beginning of the talk, division points are homology classes. So really, this is something about the homology of the modular curve and the fact that it doesn't kind of break up into a direct sum of pieces corresponding to f and g. Okay, so now in terms of actual physical points, there's a notation. If you have an elliptic curve or an abelian variety, you write, bracket 2. That means the group of points that are annihilated by 2. So if you have an elliptic curve and you take the two division points on the elliptic curve, there are 4 of them. It makes a group of order 4 that's the Klein 4 group, z mod 2 cross z mod 2. And actually, when you take an elliptic curve, typically you write it, y squared equals x cubed minus ax minus b. The two division points are the point at infinity together with the 3 points on the x-axis where x cubed minus ax minus b happens to vanish. So the 3 roots of the cubic polynomial in x. So it's kind of easy to see there are two division points on an elliptic curve. And in this case, the 4 division points of f coincide with the 4 two division points of g inside the abelian variety J037. So that's an example of how Hecke operators form a congruence because they're forced to. They're forced to somehow by the presence of this obstruction to having a direct sum being the Jacobian J037. And so what we'd like to think is that this happens much more generally. So much more generally, you can talk about an elliptic curve over Q. You can start by saying, well, it's defined by some cubic equation, and then you bring in Wiles and Taylor-Wiles, and you say, oh, well, this elliptic curve is actually covered by x0 of n for some n. N specifically is the conductor of the elliptic curve. And you can look at the pullback map from E to the Jacobian. And the pullback map, as I've already said, is not necessarily an embedding, but if you replace E by the image of the pullback map, then you kind of restart the whole construction and the pullback map becomes an embedding. You kind of make it so. So this is the step of replacing E by an isogenous elliptic curve. If necessary, elliptic curves come in clumps. Elliptic curves are said to be isogenous if they differ from each other by finite groups. And what Taylor and Wiles proved is that modular forms of a certain type, the ones that are Hecke eigenfunctions and have integer coefficients, are in one-to-one correspondence with isogeny clumps, isogeny classes of elliptic curves over the field of rational numbers. So you can get the elliptic curve stuck inside of J0 of n, and then you want to have, that might be the analog of E sub f. And then what's the analog of E sub g? Well, you have to back up for a minute. It's not going to be an elliptic curve because the modular curve might have genus 1001, in which case the analog of E sub g is going to be an abelian subvariety of dimension 1000. It's not going to be an elliptic curve anymore. And what it is just the kind of orthogonal to E inside the Jacobian. That makes sense by Poincaré because Jacobians of curves have a natural autoduality. And then when you take the intersection of E and its perpendicular, its kind of complement, you get something that represents the obstruction to the Jacobian actually being a direct product of two geometrical things. And if you figure out what the thing looks like inside of E, you will realize that it's a group like EF of 2 before, a Klein 4 group. It's a group that's a product of two cyclic groups of some number order D. And what is D? Well, actually, D is the degree of this map. If you have a covering map between algebraic curves, non-constant, over every point of the target, there are going to be a certain number of points of the source, and if you avoid ramification points, that number is constant. That's the degree of the covering. And modular curves, these are called modular parameterizations. They have a fixed degree that you can compute using SAGE. So that's, a really great thing. If you have an elliptic curve, you can apply the function modular degree, and you get a positive integer and figure out what this thing is. And let's go back to trying to interpret what happens. There's going to be a theorem that congruences come from geometry. And how do we do this? Well, we have to reboot yet again. Maybe this is chapter 2 or chapter 3, the same sort of construction. What we do is we introduce the ring of Hecke operators that are acting on the Jacobian. So if the modular curve has genus 1001, the Jacobian has dimension 1001, and this ring is a free Z-module whose rank is 1001. It's a very big ring, and it has a natural quotient Z, which you get by restricting the operators to the elliptic curve, and each operator gives a multiplication by an integer. Those are the only endomorphisms, actually, of an elliptic curve over Q. And then the action of T on the other abelian variety, the thing that has dimension 1000, will give you a quotient of T that's some very big ring. It's some kind of unknown commutative ring of rank 1000 over Z. And by the way, one thing that I really admire in Barry Mazur's Eisenstein ideal paper is that was the first article that really asked the question, when you have these rings, T and the image here we'll call T prime, what are these rings like from the point of view of the theory of commutative rings? No one had ever done that before. In fact, it was quite common in the subject to take the ring and kind of shake it around by replacing it by some ring that was a little bit bigger than it, by some finite index, and then that might have a simpler structure. But the question was, what's the structure of the original ring? And this was a highly productive question because it launched a lot of activity where people try to figure out what was going on. So anyway, you have these two quotients of the Hecke ring. You have Z and then some other quotient of rank 1000 or something. And the question is, how far is T from being the full product of these things? So to the extent that it's not a product, there's some congruences going on. Basically, congruences between the modular form associated with F, with the elliptic curve, which is one modular form, and then the modular forms that are associated with the complement, and those could be, basically, if you allow conjugations and so on, 1,000 of them. There could be, as many forms as there are the dimension in this complement. So we're looking for congruences of some kind, and these congruences are measured by the failure of T to be the full product Z cross T prime. And there's an ideal that you can introduce to try to measure this. It's the ideal that you get by looking at those Hecke operators that vanish on the E perpendicular. So all the ones that are 0 in the second factor, so those in the product have the form, T comma 0 or something. And then you project to the first factor, you get an integer, and the question is, what integers do you get? So these integers fill up some ideal of Z, and this ideal is called the congruence ideal. It's a principal ideal because we're just looking at the ideals in the ring of integers, so you could say that it's generated by some positive integer, and that positive integer, roughly speaking, tells you the extent to which there are congruences between F and other forms in the complementary space. And then there's a relation between C and D. So C basically tells you all about the congruences between F and everything else. And what is D? Well, D occurs over here, if I can get to it. It's the extent to which congruences are caused by a physical obstruction for the Jacobian to be a product, namely the intersection of these two complementary factors is E of D. And the relationship between E of D and C is simply that the ideal C is contained in the ideal D. That means that the number D divides the number C. C consists of all congruences, and D consists of those congruences that arise from the obstruction for the Jacobian to be a product. And if you think that congruences should arise from geometry, then the theorem would be that these two ideals are equal. Okay, so maybe I'll skip over this because I've basically said in words what's going on. D measures the congruences coming from geometry, and C measures the congruences coming from observation, the congruences that you actually see, those that are geometrical, and maybe others that we can't readily understand by geometry. And if you want to say it in some rigorous way, it's a kind of a nice thing to do. C is the ideal consisting of integers that come by restriction from operators that vanish on this abelian variety of dimension 1,000. And D is the ideal consisting of things that vanish on some little finite product, which is inside of E perpendicular. And the idea is that anything that vanishes on E perpendicular vanishes on this little product intersection. And so that's the way that you get the containment that C is contained in D. And there we go, that's the containment. Okay, so there's a theorem which we can prove, but there's a little bit of notation. I wonder if I should insist on it or maybe skip over it very quickly. It's just that when you look at these ideals, the ideals are in Z, and Z is part of a product, Z cross T prime. It's the operators coming that are gotten by restricting to the elliptic curve together with the operators that are gotten by restricting to the complementary factor. And when you think of Hecke operators in T, T is in a product, you can think of them as pairs, T comma something. And the D will consist of those integers T such that T comma 0 is actually an endomorphism of the abelian variety. If you have an endomorphism, a product of endomorphisms of the two complementary factors, you get an endomorphism if they agree on the intersection. And to say that they agree on the intersection is to say that T vanishes on this E intersect D perp, which is of order D squared. So that's where the D comes from. And the C is, by definition, the set of things that you get by restricting operators that are zero, entirely zero on the second factor. And so what happens here is that the Hecke ring is a ring of operators on the Jacobian, and so here this ring is inside of Nj, and then if you look at these two equations, you get another reason to understand that C is inside of D. So these are a priori phenomena, and then what we're going to try to do is see to what extent this inclusion is actually close to being an equality. And the answer is that the geometry does not explain everything. I've been pushing the idea that when you have congruences, you can explain them by something geometrical, and at least in examples, the geometry that comes to mind does not explain everything. So here's a numerical example. We take an elliptic curve given by that complicated looking expression. I think, no, that's actually correct. Maybe it's y squared plus xy plus y on the left. This is the simplest elliptic curve written in its canonical form, whose conductor is 54. So we've had 37 and 691. This is conductor 54, which is not very big. And then it turns out that the modular degree is 2, so the congruences that are coming from geometry have d equal 2, whereas if you look at all congruences, there's also a congruence mod 3. the congruence number is not 2, it's actually 2 times 3. And this kind of is a cautionary tale that tells you that geometry is not going to explain everything. But if you're kind of looking for clues, the fact of the matter is that 54 is divisible by 9, and 9 is 3 squared, and the 3 is the extra factor here going between 2 and 6. And that's actually the key to understanding this type of example. Before I get to the theorem, I want to point out that there are huge tables of these numbers that were compiled years ago by Stein and some of his collaborators when they first started SAGE and got it going to work very fluidly with modular forms. And once again, you know, this is a subject where a lot of the phenomena that were uncovered and then proved actually came from numerical calculations, which kind of explained what seemed to be going on. And the theorem, which I proved, I don't know, you know, 10 or more years ago with William Stein and Ahmad Agashe, is that, well, D divides C, and the ratio involves only primes that, such that the squares divide the conductor. So 54 has a square factor, namely 9, and that explains why C over D is permitted to have a factor 3, and in fact, in this numerical example, it does. And maybe what I'll do is just close by explaining a little bit about what goes into the proof of the theorem. As I tried to explain a few slides ago, let me go back here, if you want to link up C and D, you're talking about the distinction between a, whoops, that's the wrong button, between a Hecke ring and the ring of all endomorphisms of the Jacobian. And in fact, you know, you could start by doing some philosophical discussion. You could say, well, this Jacobian comes from modular forms, and the Hecke operators are those operators that come from the modular forms. So maybe all of the endomorphisms of the abelian variety actually come from Hecke operators. And that's a kind of good impulse to have, but it turns out that this is not literally true. In the case when n is prime, Barry Mazur proved that the ring of Hecke operators is exactly the full ring of endomorphisms, but that's because in that case, here's the shameless self-promotion, I had proved that T and Nj were equal up to finite groups, and Mazur had this brilliant argument to show that the finite group that kind of mitigated between end of J and T was actually the trivial group 1. So the fact that T is the full ring of endomorphisms in the case when n is prime is in some sense a theorem that I proved not jointly, but kind of in 2 steps with Mazur. But it's very misleading because in general, there are lots of endomorphisms of the Jacobian that don't have anything to do with Hecke operators, and that's because the Jacobian often has repeated factors, and then you get kind of matrix rings operating on it, whereas the Hecke ring is commutative, and so you're getting something that's a lot smaller. And the correct theorem is that if you look at the quotient of the endomorphism ring by the Hecke ring, that can be very big. It's kind of typically, you know, of positive rank, but it doesn't have any torsion. So that's the idea. What Mazur basically proved is that it doesn't have any torsion, and in terms of the jargon of the subject, that means that the Hecke ring is saturated in the ring of endomorphisms. If some multiple of an endomorphism is a Hecke operator, then already it is a Hecke operator. And basically by translating Mazur's arguments to the general setting, Agashe and Stein and I were able to prove this saturation property that it just translates by copying the proof locally away from the primes whose squares do not divide the level. So we can't prove it for the 3 primary components, which is very good when n is 54. It's very good because the theorem is false, but we prove it for all the other components, and you can verify this by looking at the tables. So I'm going to stop now, but I do want to say that there's a connection between this subject and the very beginning of the talk. You can take this subject and try to explore what happens when you consider not just the Jacobian, but something called the Generalized Jacobian, where you use a set of marked points to make the Generalized Jacobian, and you take those marked points to be exactly the cusps. And if you kind of continue on with this type of argument, you end up proving that something called the Eisenstein ideal, which is an analog of this congruence ideal generated by C, is the ring of, it's the ideal that the exact annihilator of the cuspidal group, and that gives you a lot of information about the cuspidal group. But I'll stop.
Thank you for talks. So, do you have any questions and a comment? Okay, then I have a question. So, in the beginning, you said William Stein, he made a program with the Sage, something.
Sage.
Sage, yeah. Is that tells about something J0n, not the Q, instead of any number field, the K torsion point also.
So you want to look at K torsion and not just Q torsion.
Yeah. So and then if you replace by that extension Q, then is it possible equality with the C?
Yeah, so there has actually been some preprint that I didn't mention by a group of Indian mathematicians. The cuspidal group is all, every point is defined over a cyclotomic field, and it might be natural to look at the torsion points of the abelian variety over that cyclotomic field and see if they're cuspidal. So one thing about Sage, just a kind of general advertisement, is that every time Sage does something wonderful, mathematicians come along and say, well, hey, it would be better if it did this, this, and this in addition. And then what happens is that the Sage group organizes these Sage days, which are intensive workshops, where people get together for about a week and they try to augment the code so it handles the type of questions that mathematicians wanted. So I think it's a really great software package because there's kind of direct communication with what people want.
I see. Any more questions from it, please? All right. So let's thank the speaker again.